Hi students. So in this video we study the important continuous probability distribution, which is called as normal distribution. Normal distribution. Now we know that it is a continuous probability distribution. So in the previous exponential continuous probability distribution, we have already known that to consider a continuous probability distribution, we consider only the probability density function of that distribution. Let us consider x a continuous variable. Okay, and consider two constants which we take it as mu and sigma, where condition on mu is it is between minus infinity to plus infinity, and sigma greater than 0. And if we consider a function in this continuous variable x, which is of this form, denoted as n of x or n of mu comma sigma comma x, which equals to 1 by sigma into 2 pi into e to the power of minus 1 by 2 into x minus mu by sigma whole square, where x can take any value from minus infinity to plus infinity. Now, if this is a function and we can show that this function satisfies the condition that it is always non-negative and the integral minus infinity plus infinity of this function is equal to 1, and this function is called as probability density function, and the corresponding distribution is called as normal distribution. That means normal distribution is nothing but a distribution which is a continuous one in the continuous variable x, having this function as the PDF. Okay, then since the PDF is that to satisfy these two conditions. Okay, now look at the constant which are used in this normal distribution function or PDF of normal distribution function, mu and sigma. We're already familiar with these constants where mu stands for the mean and sigma stands for the standard deviation. Exactly here, mu is nothing but the mean of this distribution. We can show that using the gamma function, and sigma is nothing but the standard deviation. Okay, the derivation is not included in the syllabus, therefore just remember that mu and sigma are the mean and standard deviation of the normal distribution respectively. Okay, now we'll move on to finding probability over an interval, and we know that probability over an interval is there with this notation p of, let's consider x1 less than equal to x less than equal to x2, which is nothing but the x is the continuous variable, which is a normal variable. Okay, so x is nothing but normal variable. It is also called as normal variate. Then probability in the interval x1 to x2 is given by the integral x1 to x2 n of x dx, which is nothing but, substituting for n of x, we are getting integral x1 to x2. The function n of x is nothing but this one, 1 by sigma root 2 pi into e power minus 1 by 2 x minus mu whole square. Okay, that means 1 by sigma into root 2 pi e to the power of minus 1 by 2 into x minus mu by sigma whole square dx. and this integral value will give you the probability over an interval x1 to x2. Of course, I have taken the continuous, the closed interval here, but the continuous variable x, it may be open or it may be half open, half closed. Okay, that we already learned. Okay, now the question is how to evaluate this. We know that a definite integral of this form gives area below the curve y. Here the y is nothing but this function. Okay. Now if you consider the graph of this function, which is nothing but n of x, and the graph you're going to get like this, which is nothing but the normal curve. The graph you're going to get like this. This is the x-axis. This is n of x-axis or y-axis. Okay, and this is the curve which is symmetric about this line, and this line is nothing but x equals mu, and this we call it as normal curve, which is symmetric about the line x equals mu. Now the question is, what is this integral will give us? This integral will give us the area below this curve, normal curve, this curve, from x1 to x2. x1 may be here, x2 may be here, or you can have x1, x2 somewhere here. x1 may be here, this is maybe x2. Then this integral will give this area, this much between that. Okay, now how to get that one now? Here we can't evaluate this integral because of the reason that this function you can't integrate. That's why we make use of ready reckoner called standard distribution, normal distribution table. Okay, from that we are getting this value of this integral. Of course, not directly. First, we have to convert this integral to some other integral. Okay, for that we have to use the substitution, namely x minus mu by sigma. Exactly what you find here. This you have to take it as z. If you take this as z, then we are getting x minus mu equals sigma into z, where this mu and sigma are constant. Differentiating, you are getting dx equals sigma into dz. Okay, now, so let us assume that for x equals x1, the lower limit. So we are getting z1 as the lower limit. For x1, x equals x1, z1 you are getting the lower limit. For upper limit of x, namely x2, so let us assume that you are substituting here x2 minus mu by sigma. We call it as z2. That is for x2, the corresponding limit is z2. Then this integral will be transformed into integral z1 to z2 1 by sigma root 2 pi into e to the power of minus 1 by 2 into z square, or e power minus z square by 2 into sigma dz. Now the sigma cancels, and we can call this as the function n of z, or I can write this integral as z1 to z2 1 by root 2 pi into e power minus z square by 2 dz. Okay, and the z is called as standard normal variable. And this is nothing but probability on interval z1 to z2 in the standard normal variable z, where z is nothing but this x minus mu by sigma. Now, the graph of this function, okay, you are getting the standard normal curve which you are getting like this. Standard normal distribution curve is exactly this one, where this is the z-axis and this is the n of z axis, or f of z. They are written f of z, or you can write it as n of z. Okay, so this n of z. So now the curve is symmetric about this line n of z, similar to y-axis, and this you can see that minus 1 to 1, minus 2 to 3, minus 3 3. And the curve is symmetric. Now that means this property over the interval, that one is Z2, is nothing but area below the standard normal curve. The curve is called as standard normal curve from Z1 to Z2, maybe from minus 2 to 2, or any value between minus 2 minus 1 to 2, like that. Okay, or I can consider Z1 maybe here, or Z2 maybe here, or here Z1 to Z2, like that. Okay, just area below that one, okay, in that interval. Fine. Now, so how to find out that? I already told you that we are making use of table called standard normal distribution table. Standard normal distribution table. Using this we are finding property over the standard normal variable z from z1 to z2, which is in turns gives the property over the interval standard variable as normal variable x from x1 to x2. Now, so the normal standard normal distribution I'll explain in the next video. Okay, so I'll give you the table and I'll explain how to find out that one. Now, let us find the relation between this function, this integral, which is in the product over the interval z1, z2, and this values given in the standard normal distribution table. Okay, fine. Now, the standard normal distribution table gives area A of z or y of z, which gives exactly the integral 0 to z of n of z dz, which is nothing but 0 to z 1 by root 2 pi into e to the power of minus z square by 2 dz. And this integral is same as this integral, namely this one. Only the difference is the limits are different. Lower limit is 0. Okay. Now, these values for different value of z are given from the table. Now, to express this in terms of a of z, for that what we do? No? We are making use of the simple results. I make a list of results. Very simple, easy to follow. Okay, and if you remember them, then you can easily work out the problems here, making use of the standard normal distribution table. The results are this. The first one, a of infinity, which is nothing but integral 0 to infinity n of z dz. Okay, which equals to so just area below the curve from here to here, from 0 to z, this portion exactly the positive, and we know that the complete area equals to 1, that is integral minus infinity to plus infinity n of z dz equals 1. Therefore, this area is equal to 1 by 2, half of that, because curve is symmetric over this line. 1 by 2 you find this side, 1 by 2 this side. That means this is equal to 0.5. So A of infinity equals 0.5. Okay, second one. Now let us consider the case probability over a positive interval z1 to z2. Okay. Now this can be shown equal to a of upper limit z2 minus a of lower limit z1. The other notation for this a is phi. Instead of a, in some book they use notation phi. Phi of z2 minus phi of z1. Now I'll take an example. It's easy to understand. Okay, let's consider this from 1 to 2. 1 to 2. Okay, I'll just clear up this. Or let us take that this graph again. Okay. Now I want area below the curve from 1 to 2. Okay. I'll consider this one. So A of 1 less than equal to Z less than equal to 2. That means this area we want. 1 is here, 2 is here. This area we want. For that, what I do now, I'll take this complete area from 0 to 2, which is nothing but A of 2 minus. So from that, you have to delete this portion, that is from 0 to 1 is A of 1. Okay. So you do not write this graph, you do not consider the graph. Just remember that probability over in a positive interval z1 to z2 equals a of upper limit minus a of lower limit, or phi of upper limit minus phi of lower limit. It's clearly explained in this figure. Okay. The next result is this. Probability over the negative interval. I'll take minus z3 to z4. So it is nothing but probability over positive counterpart of this interval, which is z4 to z3, which is the positive counterpart of this interval. Because the curve is symmetric about the line n of z that is on the positive and negative side. So then it is the previous result, which is nothing but a or phi of upper limit z3 minus a of lower limit z4. Okay. So if you want to understand, I'll consider the graph again. Okay. So I'll consider the graph, standard normal distribution curve uh, from minus. I'll take an example. So probability from, let us take minus 2 to minus 1, or minus 3, rather minus 3 to minus 1. That is from here to here. This area. This is same as this area. Curve is symmetric. 1 to 3. Therefore, we can write this thing as probability from 1, negative of this becomes 1, minus of minus, less than or equal to z, minus of this, that is 3. Okay, that's this area from minus 3 to minus 1 equals 1 to 3. Now, you can easily use the result that A of 3 minus A of 1, that is complete area minus this area you have to cut off. Okay, next result is fourth one. Probability from negative value, that is minus z5 to z positive z6. Okay, this is nothing but we can say it is equal to a of z6 plus a of z5, where z5 is nothing but absolute value of minus z5. Minus z5 is negative, z5 is positive. Okay, so I'll take an example for this also. So let us consider the probability from minus 1 to minus 2, sorry, plus 2. Let's consider this as an example. That is minus 1 is here. Okay, 2 is here. So this area, complete area we want. So we can split as this minus 1 to 0, this portion, then 0 to this portion, and minus 1 to 0 is 0 to 1. That is nothing but a of 1, and 0 to 2 is a of 2. Therefore, this can be written as a of 2 or phi of 2 plus a of 1, which is nothing but the same as other notation, phi of 2 plus phi of 1. Okay, so if we just remember these results, that is a of infinity equals 0.5, first result. Then second result, probability over a positive interval z1 to z2 is a of upper limit minus a of lower limit. Explain this example. Next result, probability from negative to negative interval minus z3 to minus z4 is nothing but probability over the positive counterpart of that. That is, you take absolute value of this, that becomes lesser than absolute value of this, then it reduces the previous result, probability over a positive interval, which is nothing but a of upper limit minus a of lower limit. Next result is probability over negative to positive interval. Okay, it comprises a part of the negative interval and positive interval. It is simple. It is nothing but a of upper limit plus a of absolute value of lower limit minus z5 becomes z5. Let us explain this example, minus 1 to 2 if you want. It is a of upper limit 2 plus a of. So using these four results and converting probability over the variable x, okay, in the interval x1 to x, to probability over the interval z1 to z2. For this, we have to use the substitution, that is x minus mu by sigma equals z. Use the substitution, then this is converted into probability over interval standard normal variable z. It's probability over an interval x1 to x2 in the normal variable reduces to probability over the standard normal variable z from z1 to z2. Okay, z1 z2 need not be positive. It's a combination. Okay, different combination we discussed earlier. So using the substitution, then we are writing this in terms of a of z, a of z. Okay, using these four results, 1, 2, 3, 4, and these values a of z or phi of z are given from the table, which is called standard normal distribution table. Using that, we can easily work out the problem. Therefore, the problems are simple here. Just for the problems, we are using that standard normal distribution table, or simply normal distribution table. In the next video, I'll teach you how to use the table and how to evaluate the problems. Okay, in the next two videos, we learn or we work out all kinds of problems so that we learn how to evaluate probability over a normal variable x by making use of the substitution and converting into probability over the standard variable z and making use of the standard normal distribution table. Okay.